The lesson today is going to be talking in section 8.1 as we begin chapter 8 about exponential and logarithmic functions. Our goal today is to focus on exponential growth and decay, what the graphs look like, and how to derive a graph in a couple different ways. Our first graph as we look at is y equals 3 to the x, and this is an example of an exponential function. And an exponential function, as you can see, is a situation where we have the equation in general of y equals ab raised to the x. And so most of our exponential functions will have this situation. In this case, we have y equals 3 to the x. And so here we have a equals 1 and b equals 3. And so as you can see, b, since it is greater than 1, this is an example of exponential growth. That means the graph is going to start low and head up something like this. So what we're going to do is we're just going to plot a couple points and into our problem. So first we go 0, and so then we're going to say 3 to the 0, and 3 to the 0, as you know, is 1. So we're going to plot that point first. That's our y-intercept, our most important point. Our second point is at 1, so we have 3 to the first, or 3. And our third point is 3 squared, which is 9, and very quickly 3, 4, 5, 6, 7, 8, 9, we're off the graph. And so you can see this rapid increase here. So we're going to go on the negative side, so -1. So 3 to the -1, as we just talked about, that's 1/3. So we're way in here. And I guess if we could also plot -2. So that's 3 to the -2. That's 1/3 squared, which is 1/9. Obviously, we're going to have to zoom way in here to give an idea of 1/9. I'm going to erase that 1/3 and put it a little bit higher. And then we're going to call this 1/9. And so what you have here is a graph that's going to start very low, close to the x-axis, but not touch it. And then it's going to come up through the y-intercept of 0, 1, and then go shooting upwards here all the way up to infinity. So this is our equation of an exponential function, 3 to the x. It starts low with a horizontal asymptote at the x-axis here, and it shoots way up top. Probably our most important point that we're going to key on is the y-intercept, and then secondly, the value at 1. All right, let's look down and see what happens when we put a number in front. Here we have a equals 4 and b equals 2. This is still an example of exponential growth because b is greater than 1, so it is still exponential growth. But let's plot some points again. Now we have 0, 4 times 2 to the 0, so 2 is to the 0, so that's 1. 4 times 1 equals 4. So now we have the point 0, 4. 1, 2, 3, 4. Once again, that's our bottom line, our base number. I don't know which our graph is going to be taken off of. We start with 1, 4 times 2 to the first, that's 8. So all the way, already we're all the way up here at 8. We can't do anything more up vertically. So let's go negative. 4 times 2 to the -1, that's 4 times 1/2, that's 2. So at -1, it's at 2. You see there's already this decreasing happening here, so let's go at -2. 4 times 2 to the -2, that's 4 times 1/2 squared, that's 4 times 1/4, and that's 1. So at -2, we're at 1. At -3, we have 4 times 1/2 cubed, that's 4 times 1/8, that's 1/2. And so once again, you see the situation where it is decreasing rapidly, and this is going to bottom out once again at the x-axis if you tried additional points on this graph. So we're going to try to draw this going up, just like so. And I hope you notice that we're not touching the x-axis, we are just approaching it as a horizontal asymptote. So these two are examples of exponential functions. They're very typical. They're all going to look very much the same. The most important point of each of our exponential functions is going to be the y-intercept. And then we're going to have the chance to see I want you to notice how the bottom example 2 kind of is closer to the y-axis as it comes in versus the top graph is a little bit more gradual coming up. But all of our exponential functions are going to look like this. So on this next page, I just want to give you some very quick examples of some exponential functions. Let's say if we have y 2 to the x. Okay, 2 to the x, that's going to go through at 0, 1, because anything to the 0 is 1. 1, 2, 2, 4. And so you have this kind of a little more gradual thing, but it's still going to come down just like so. Let's say we had y equals 5 to the x. You're still going to go through at 0, 1, because 0, 5 to the 0 is 1, but now you're going to go 1, 5. So a little bit steeper, coming down. So I hope you can compare 2 to the x versus 5 to the x, maybe a little more gradual versus steeper. We could compare this with y equals 10 to the x, still going through 0, 1, but now we're all the way up here at 10, and it's going to be very, very sharp coming down. But all of these graphs have a horizontal asymptote at x equals 0, way down here at the bottom. Let's try a final one. Y equals number 5 times 2 to the x in comparison. Well, instead of going through at 0, 1, now we're going to go through at 0, 5, and then it's going to go up from there. And so if we go to -1, it'll be at 2.5. And so you're going to come down, a little more gradual, but go up much more steep. And so as we compare these four, you'll notice the difference between 5 times 2 to the x and 2 to the x is really, it's a shift up vertically. And so the whole graph has really been pulled over tighter to the y-axis with a more gradual curve. So when you're graphing these, 3 points is usually plenty to get an idea of what they look like and moving on. And once again, this is a new word possibly at the bottom. You may have heard me use it a couple times already. An asymptote. Interesting word that there's a P in the middle of asymptote. And it's the value that the line approaches but never reaches. And in all of these cases, the x asymptote has been the equation x equals 0. Remember, that's the horizontal line at the x-axis. Excuse me, that's not x equals 0. That's y equals 0. So we have each of these horizontal asymptotes. Let's look at our next page. This next page talks about exponential decay, and we just want to identify the difference between exponential growth and exponential decay. We're still talking about the same function, y equals a times b to the x, where b is a growth factor, and if b is less than 1, it's a decay factor. All of our problems on the original situation, if you'll notice, all of our values of b were greater than 1. And so these are examples of exponential growth, where the curve is going to be going up to the right. Exponential decay, in comparison, the graph will start high, and then it will go down and go down to the right. And so this is an example of exponential decay. So what we're going to do on each one of these is we're going to identify the value of a and b. Primarily, we're going to focus on b. So here we have b equals 3. Here we have b equals 3/4. Here we have b equals 0.12. Here we have b equals 5. Here we have b equals 1/2. And here we have b once again equals 0.5. Notice the b value is always what the exponential part is working on. And so I'm just going to put growth versus decay. This is going to be example of growth. Our other ones that are greater than 1. This is also an example of growth. And then the rest are all going to be examples of decay, because all of the other values of b are less than 1. So identifying if something is growth or decay should be a very quick analysis. You're focused on what is being raised to the x. And so you're really focusing on what is being raised to the x versus the front number, the value of a. So growth versus decay, focus on the front number of x. Greater than 1, it's growth. Less than 1, it's decay. Equal to 1, the function does not grow or decay, it's just a constant. Our third little part that we're going to talk about today is, if we're given 2 points, how could we come up with the equation of in a exponential function in this form, y equals a times b to the x. What we're going to do is we're just going to use some simple algebra to try to create a system of equations that works this out. So remember, our basic form is y equals a times b to the x. And so I'm going to take my first point, 4, 2, and I'm going to plug that in, 4 equals a times b squared. Now, with that value, I'm going to take this and I'm going to solve for a. And I'm going to realize that a equals 4 over b squared. I'm going to box this, and we're going to come back to this in just a sec. Now I'm going to take my second point, 316, and I'm going to plug that in. So I have 16 equals a times b cubed. I'm also going to solve that for a, and I'm going to have 16 over b cubed. I now have two equations that are both equal to a. That means I can set them equal to each other and solve for b. And so I'm going to do that. 4 over b squared equals 16 over b cubed. This is simple to solve. We're going to cross multiply. 4b cubed equals 16b squared. We're going to divide both sides by b squared and get 4b equals 16, and divide both sides by 4 and get 16 divided by 4, which is 4. Sorry about that, little brain freeze there. Now we're going to place that and put that back into my original equation to find the value of a. So I'm going to go back to my original equation up here. 4 over b squared equals a. And so I have 4 divided by b squared. And in this case, it's 4 squared equals a. So that's 4 over 16 equals a. So a equals 1/4. We could check this by trying it in the second equation. 16 over b cubed equals a. That's 16 over 64, which is also a equals 1/4. So this means that our values of a is 1/4, our value of b is 4, and my equation very simply is y equals 1/4 times 4 to the x. And you can say, is this a value of exponential growth or decay? Well, because the b value is greater than 1, this is an example of exponential growth. Let's take a look at our second one here. Our first equation with y equals a times b to the x is going to be the exact same situation. Now we have 24 equals a times b to the negative 3. Remember that a times b to the negative 3 is really a over b cubed, so 24a cubed equals a. There's our first equation. Let's make our second equation. 12 equals a times b to the negative 2. That's 12 equals a over b squared because of the negative 2, so 12b squared equals a. Let's take these two equations and set them equal to each other. 24, excuse me, I just noticed a mistake there, 24b cubed equals 12b squared. We're going to divide both sides by b squared again, and then we're going to divide both sides by 24 and get 1/2. So my value of b is 1/2. Now I'm going to plug this into my original equation. 24 equals a over 1/2 cubed. 24 equals a over 1/8. To solve this, I'm going to multiply both sides by 1/8, and I'm going to a equals 3. We can check this with the other equation just to make sure. 12 equals a over 1/2 squared. 12 equals a over 1/4. Multiply up by the 1/4, and once again you get a equals 3. So now I have my value of b equals 1/2, a equals 3, and so I can write my equation y equals 3 times 1/2 raised to the x. So this is an example of exponential decay because the 1/2 is less than 1. Our third little part that we're going to talk about, our last little part we're going to talk about today, is using modeling in our graphing calculators to come up with an equation of a line for depreciation. And so I need you to take out your graphing calculators. And we're going to take this idea here and we're going to work through and put these values into our graphing calculator. So as we look at our points, we're going to have to identify the points on the graph that are best represented by the data that we have. And so I've given our instructions down here at the bottom that we're going to work on. So we're going to highlight, I'm just going to highlight in blue the points we're going to be keying on here on our problem as we work on our calculators. So first thing we have to do is identify what these values are. This is about 30,000. I'm going to have to say this point right here is 1, comma, it looks like it's a little bit above 20,000, so I'm going to say 20,500. This point right here looks like it's right on the mark of 15,000, so that's 15,000. This point right here looks like it's a little bit above 10,000, so I'm going to say that's the point 3, comma, 10,100. And this point down here looks like it's between 5,000 and 10,000. I'm going to say it's 7,000. So that's the point 4, 7,000. And then finally our last point down here is the point 5, comma, looks like it's right about 5,000. So we're going to take those points and we're going to have to put those into our calculator under our statistics mode. So we're going to go to our calculator. And the first thing we're going to do is we're going to go and we're going to click on the button Stat. That's right here. Now we're going to go over to Edit, and we're already in the Edit mode. And so we're going to go to Edit, we're going to hit Enter. This is going to bring up a table. And our table is L1, L2, etc. going across. And we're going to say L1 equals X and L2 equals Y. So our first value of X was 0, 30,000. So we're going to put in 0 and hit Enter. And we're going to put in 1 and hit Enter, and 2 and Enter, 3 and Enter, 4 and Enter, and 5 and Enter. And that's going to put our X values in. Now we're going to arrow over and we're going to put in our Y values. At 0, it was at 30,000. At 1, we have to remember that we said that value let's see what we said that was at. At 1, we said it was at 20,500. 20,500. At 2, we said it was at 15,000. At 3, we said it was at 10,100. At 4, we said it was at about 7,000. And at 5, we said it was at 5,000. Now, those numbers are not, you don't have to have the exact same numbers as me, but we're trying to have a best estimate as we put that data in. All right, our next thing that we're going to do is we're going to hit the button Second and then Stat Plot. And Stat Plot is right up here above the Y equals. And so Second, Stat Plot, and that's going to take us into the Stats function. We're going to choose option 1, which is already there, and then we're going to press Enter. And that's going to bring up our Stat button. Now, you need to go up to the top here, on top of this where it says Plot 1, and hit Enter. And you need to make sure that is black and selected, and then go down to where it says On Off and hit Enter again to make sure this is turned on. My graph has a simple, I'm going to have my graph be just a very simple dotted there, and X1 and Y1 are my lists, and my mark is just going to be some boxes. My graph is going to be in blue. So you could change those things if you wanted to, but you don't really have to do that if you need to. Next, we need to figure out what my window needs to be for my graph. So my window, remember, is going to be based on my data. So I'm going to have my X-min be 0, and I'm going to have my X-max be 6. Actually, we can have that be 10. That might give us a better window there. I'm going to put a tick mark on the scale of down 1 through 10. My Y-min I'm going to have be 0, but my Y-max I need to be way up there, so I'm going to say 31,000. And I don't want to have 31,000 tick marks, and so I'm going to take my scale on my Y values and turn that off completely. So now we've set our window. Once we've set our window, we can push the graph key, and we're going to see a graph of the data that we have that's going to be what we anticipated and plugged in to our problem. The next thing that we're going to do is to try to get a feel for what this looks like. And so now we're going to hit the stat button, and now we're going to go over and calculate what these values are. So to calculate what these values are, we're going to go down to option 0. So you can either arrow down all the way to 0, and 0 is exponential regression, or you can just push the button 0, either one. And now our exponential regression, this is going to calculate the values of A and B for us, instead of having to go through an algebraic thing. Now, we're going to do something kind of cool here, and we're going to have it input it into the Y value for us. So to do that, we're going to hit alpha, trace, and we're going to choose Y1. Then we're going to go down to calculate, arrowing down, and we're going to push the value calculate, and it's going to instantly calculate the values of A and B for us. So the value of A, as you can see, is 29,904, and the value of B is 0.6981. So those are pretty accurate, I would say, and to use. And now we can go back and we can go to our Y value, and we can see this overlay on it. So go to Y equals, and what it did was it inputted in the values instantly because we've stuck it into Y1, and here you can see those values into our equation already. We want to make sure the equal sign is turned on here on our Y value, and it's black, and it is. And so we're going to overlay this graph on top of our dots. So now you can hit the graph button again, and you're going to see this line overlay directly on top of our dots, showing this is a pretty good graph based on our statistics. Maybe one of them's a little bit high, one of them's a tiny bit low, but in general, this is a pretty good graph for us. So what we can now do then is we can take this information and we can translate it back, and we can say, okay, we need to then what is the value of A and what is the value of B? Well, if you remember, the value of A was 29,904, and our value of B was 0.6981. So my equation then is Y equals 29,904 times 0.6981 raised to the x. And our last question is, what would be the value of the car at year 6? So here's year 5, here's year 6. It's kind of hard to see what that is, but now we can use our equation to really calculate that accurately. And so we're going to go back to our graph, and we're going to take a look at this, and we're going to say, okay, at the value x equals 6, we have to think, what is that going to be? Well, it's hard to tell just by looking at the graph, but what we can do is we can go to the table function. So we go to second table, and this brings us into a table of all of our functions. You may not have realized this, but here are all the values that we have. So I'm going to arrow down to x equals 6. And here we see the value is, very simply, it says approximately 3461.9. So the approximate value for our car after 6 years is 3461.90. So this is an example of using data and using our calculator to compute an exponential depreciation scale for this. We're not going to go and look at the second example here, but it would be very similar. You would put in the data points, 0, 12,000, 1, and whatever you thought that was. Let's see if that's 10, that's probably 11. That's maybe just under 10, a little above 8, a little below 8, and you could do the exact same thing for practice, putting in these points. I hope this has been helpful. As we look at our homework, just to kind of overview, you're going to do some quick sketches on 1, 5, and 7. Plot maybe 3 or 4 points. On 10 and 14, you're going to compute the values of A and B, like we did on our example as well. On 16 through 23, you're going to have to tell whether it's growth or decay by focusing in on the B value. And then lastly, you're going to use your calculators for 32 and 34 to come up with an equation that will best illustrate our depreciation situation here. And then once you have that equation, evaluate the function for x equals 6.